Now that you have an understanding of the scientific method, as well as the vocabulary words associated with the relative confidence that we have between things like hypotheses and theories, we can move on to discussing how the earth formed. And it's very important, of course, that you understand the mechanisms involved, what were the physics involved. But it's also important for you to understand how scientists obtain this information. Why do we call things a theory? And why do we have certainty about that? So it's important to look at both of those things. So, what we'll do in this lecture is we're going to build a timeline. We're going to go through some of Earth's major events here. So, take notes alongside the lecture with me because these numbers are going to be important and they will be on your midterm or your first exam. So, here I have written, this is shorthand. Because in earth science we're dealing with really old stuff, Earth itself is 4.5 billion years old. We have this shorthand notation so we don't have to write out all those zeros every time. So here we're going to outline the major events that we care about in an earth science class. The formation of the universe, our local solar system, and then the formation of Earth and its oceans. And then we'll also discuss how we know that, right? How did scientists prove that, and what's the evidence outlining that? So let's start at time zero, right? So you guys may have learned about the Big Bang before in class. And this episode of cosmic inflation began at 13.77 billion years ago. So let's jot that down first. And just so you know, I'm going to use these as approximate. So we're just going to say 14 billion years ago. Okay, that's the formation of the universe. Because we know our solar system is one of thousands and thousands, right, within our galaxy, which is in encompassing a universe of thousands of other galaxies. So we have to start somewhere, so we start at time zero. So the universe itself has been around for 14 billion years, but Earth is much younger than that. So I have some other videos that will accompany this lecture that will give you a much better visual idea of how the Big Bang operated, how the expansion of the universe created galaxies, etc. So make sure you watch those other YouTube videos because they're really good at giving you the visual side of looking at these types of processes. But in a nutshell, if you took all of the matter or stuff in our known universe and you pushed it all back together into a tiny infinitesimal speck, that would be the conditions before the Big Bang, right? So prior to the Big Bang, before time existed, you had all of the matter in the universe compressed into something called a singularity. And at one point, at 14 billion years ago, that singularity all of a sudden began to expand rapidly. And so you can see that demonstrated in this image here. Right, starting out from this point here, we have cosmic inflation. So we can see we have the development of galaxies and planets form as the universe cools off. Because in the beginning, it was very hot and we didn't have a lot of the elements that we have now because the universe was in a hot, chaotic stage. So as it cooled, it continued to expand. And it's expanding even today. It's continuing its expansion from the Big Bang. So we're getting perpetually further away from our bordering galaxies. So the Andromeda galaxy is moving away from our Milky Way galaxy. And so the universe is still expanding. So that's one way scientists figured out the Big Bang, because everything is moving away from each other. Okay, so now we can zoom along the timeline here to the formation of our local solar system. So in this class, we're going to learn a lot about Earth's mechanisms and how Earth formed. And then during the last lecture, we'll also talk about the other planets. But I saved that for last because it's important we understand basic processes before we go to explore them on other planets. So the formation of the solar system, the best explanation for this is the nebular hypothesis. So this is important. Look at the words that are highlighted here. Hypothesis. What does that mean? That means that it's not a theory. So it's not a scientific fact. It's just our best guess. Whereas if we go back to the Big Bang is a theory, which means it has been proven and it has a scientific consensus majority. It's quantifiable. But for the solar system, our best guess, and it's a pretty good one, we have a lot of evidence, is that our sun is the recent most sun in a series of supernova explosions. So before our sun, older sun went supernova and exploded. So stars have a limited lifespan, they don't live forever. And from the ashes, kind of like Harry Potter with the fox, the phoenix, right? Every time he gets too old, he blows himself up and becomes a baby phoenix again. It's the same sort of analogy. And then gravity pulls everything back together. It concentrates material at the center of the cloud. And so once the sun was born, then we can have additional stages in solar system development, looking at things like the formation of oceans and life. So make sure you watch these videos. They are linked in Canvas for you to get an idea of the mechanism involved and how we know about this hypothesis. Let's revisit our timeline here. Okay, so we have the formation of the solar system. This was roughly 4.6 billion years ago. Formation of Earth was very shortly after, roughly around 4.5 billion years old. Okay, so we've got our timeline here. So before we talk about the formation of Earth and Earth's oceans, let's talk about the how we know about the Big Bang Theory and the age of the universe. I've already sort of talked about how we know the galaxies are continuously moving farther apart. But the most quantifiable way we have proof of the Big Bang is something called cosmic microwave background radiation. And in Big Bang cosmology, this is basically, it's like fossil radiation. It's electromagnetic radiation that's a remnant from the early stage of the universe. And the CMB, it's faint, right? But it fills all space in our universe. So we can look at a picture of it actually here. Here we have an image of the universe. So that radiation penetrates the whole area. It's basically how we have a map of the extent of the universe to begin with. So this relic radiation is like a scar, basically. And it's roughly 14 billion years old. So in science, in order for something to go from a hypothesis to a theory, it has to be proven, right? It can't just be the best guess. There has to be something like this, something like cosmic microwave radiation that is, measurable. And back before we had digital television, if you had some of the old school televisions, occasionally you would get static. Or if you're, in the car and you're flipping through the radio stations, you'll hear some static, and you can actually tune into that radiation, the cosmic microwave background radiation, and listen to the Big Bang, basically. So that's pretty cool. And I remember when I learned that in college, I thought that was pretty neat. So I wanted to share that with you guys. So now we have our time scale is forming here. Let's jump back here to looking at the solar system and Earth. So the early Earth, or proto-Earth, was a lot different than Earth is today. It was a lot larger, it was a lot hotter because, it's still new. It's just, been born of the chaos of a supernova explosion. And so all this material has coalesced together very rapidly. There's a lot of heat energy. And so because of that, early Earth was much hotter. The surface of the planet was like a magma ocean. There was no solid crust yet. And the composition started off as homogeneous, which means that there was no differentiation or layering. It was kind of one big ball of similar density. And during the early bombardment, so right after the supernova, things are still, getting put together. Earth was bombarded by a lot of meteorites, right? So the moon has very good evidence of that. If you look up in the sky, you can see the craters in the moon. And the reason that we don't see that on Earth is because Earth has something called plate tectonics and the moon doesn't. And this is covered in the next lecture. Plate tectonics is why we get earthquakes and volcanoes. It's the reason why Earth's surface is active. Basically, we have an outer shell of our planet that doesn't stay still, and plates move around the Earth over a magma ocean and create these energy and friction that cause earthquakes. But the moon's outer, crust and outer core doesn't seem to be liquid. So because of that difference, that's why the appearance of the moon is very, very strikingly different to our Earth. And so back when Earth was born around 4.5 billion years ago, we also had the moon formed shortly after. So the moon formed somewhere around 4.45. You can just take notes, around 4.5 billion years ago. There was a body the size of Mars that collided with Earth, and the ejecta from that collision coalesced to form the moon from gravity. So the early Earth, it had an atmosphere, a small atmosphere, but that was originally boiled away and blown away by the solar wind. So before Earth had a magnetic field, its atmosphere was very vulnerable to solar wind. And you may have heard before, in some of your other science classes, that Earth is very specially fine-tuned for life to exist, right? So it's no coincidence all of these events, the collision that formed the moon, all of these things eventually led to Earth being a very stable, habitable planet. So there was a lot more heat also from something called radioactivity. And so we're actually going to talk a lot about this when we learn about how scientists date the age of rocks, right? How do scientists put a rock in the lab and know how old it is? How do they put a number on that? We're going to learn about that in one of your historical geology lectures. But because Earth was cooling now, post-birth, it contracts. And eventually it did become layered over time. So as things cooled, you had the heaviest stuff all sink down to the center of the planet. This is called density stratification. So all of the most dense stuff, such as the iron and the nickel, sank to the center, whereas the least dense stuff, the light stuff, the silica-rich rocks, they rose to the top, right? So Earth differentiated based on that cooling. And so when we have your first exam, you'll need to know the layering here, right? So Earth is divided up into different layers based on both composition, i.e., what is it made of, iron, silica, and also its thermodynamic properties. So is it rigid? Is it a solid? Is it a liquid? Is it plastic? So this is important when we talk about things like volcanoes and earthquakes later on in the class. The reason why we have an active outer surface is because our rigid, solid plates sit on top of a less rigid mantle. So the mantle is more plastic, it's more ductile and malleable. You could think about it like how you could apply strain to a ruler and bend a ruler. Whereas the outer crust, it's more rigid. So those thermodynamic differences allow for the activity that we see at Earth's surface. So here that's divided up. You can see we have the crust, the outermost layer, low density, mainly silicate minerals. The mantle that sits below the crust, mainly iron and magnesium silicate minerals. And then the core, which is the high density stuff, mainly iron and nickel. So after Earth differentiated and started to become layered, we have the slow formation of the atmosphere. So Earth's atmosphere is thought to have formed through something called volcanic outgassing. So early Earth was much more chaotic, much more hot. There was a lot more magma. And so volcanoes, things they're emitting are things like water vapor, carbon dioxide, hydrogen, other gases such as methane and ammonia. And so, as you can see, some of those gases include water vapor. And so, eventually, that water vapor condensed to form rain, and it rained for thousands and thousands of years. And so, all of the water filled in the lower laying areas and formed Earth's oceans. So, the formation of the atmosphere and oceans was around the same time, around 4 billion years ago. So, we need to write that down on our timeline here. So the oceans didn't appear right away. It took a while, around 500 million years, for them to get going, for the Earth to cool off enough for water vapor to be able to cool, condense, and form rain. So here that image is demonstrated. You have H2O vapor, other gases being expelled from these volcanoes. Eventually Earth cools off enough and you form rain. That water fills in the lower laying areas. Okay, so this lecture covered the early timeline. So now in our next lecture, we'll come back and talk about how this differentiation, how this layering of Earth contributes to the main physical mechanism that we see, which is plate tectonics. And make sure you watch all of the other videos linked to Canvas for this lecture on the formation of Earth so that you don't miss anything.